All right, just quickly rolling through solving 3 by 3 linear system. So a general 3 by 3 system in variable x, y, z has the form, this is our 3 like equations. So these will look like our equations of a plane. Similar to what we did in relationships of lines, that section, we can change these into an augmented matrix like this. So all the coefficients become these. This is our x column, this is our y column, this is our z column, and this is our constant column. Okay, we can then use operations to reduce it down to echelon form. In echelon form, there is a triangle of zeros in the bottom left corner, so we're looking at this 0 here. And then because of this, it means this is our z column. We've got h times z equals I. So our final row, h, z equals I, where h and I are real numbers. If h equals 0, we have a unique solution. If h doesn't equal 0, we have a unique solution. It means we can solve it. We just divide by h. If h does equal 0 and I doesn't equal 0, we have 0 times z equals I, where I can't equal 0, which is impossible. Hence, there is no solution, and we say that the system is inconsistent. If h equals 0 and I equals 0, similar to like parallel lines, this sort of solution here was what we got when we had 2 lines were parallel. This solution here is what we had when 2 lines were coincidence. So if we have h equals 0 and I equals 0, there's infinite solutions. And so we write the solutions in the form, we make z equal t, and then we go solving back from the second row forward, which is the example I've picked below. So you'll notice I've written some of this, and that is because I started this solution and I messed up one number. So what I will tell you is, in your graphics calculator, I always suggest if you're doing these, that you go into the run matrix mode. No, not run. You press F3 for matrix, and then you set up your, for these they're 3 by 4 matrices, and then when you're inside the matrix you do your row operations in there at the same time. It just means you don't mess up the numbers like I have here. So I'm in this section here and I've typed in my matrix here. I'd suggest you do the same. So I've put it exactly like this first one. And if I was solving this algebraically without a calculator, I want a leading 1 up here. That makes it the easiest way to solve. So I'm going to swap row 2 and row 1. And so I should have an arrow both of it. So in this particular one, you can go row operations and swap, and we're going to swap 1 and 2, and I execute that, and I've got my leading ones at the top. Now, you should notice here, the next line we want, well, row 2, we want the second row, sorry, I'm up here. I'm going to want this row 2 to be minus by 2 times row 1, so there's a star row plus button, that's the one I'm going to use. And so I'm going to times row 2, so I'm going to put a -2 in there. And then I'm going to type 1 and then 2, and I execute that, and I get this then becomes, have I stuffed that up? What did I get, -3? I did stuff it up. 2, -1, 1, hang on a sec, and 5. And so my row operations here, I need -2, row 1, and then that's times row 2, execute that. Sweet, so I get 0, 3, negative, so this now becomes 0, -3, 3, and 1. Now I've got to do my second one, so I type in, so when you're in the calculator screen, it'll have k times row m plus row n, so my k is -3. My m is row 1, so I'm going to change that to 1. And then n is 3, and then I press execute, and I've got 0, -6, 6, and 2. The next line here we're going to do, well, row 3 is going to be -2 row 2. So if I go, row 3 is -6, -2 times 3 is +6, they become 0. My next line here is row 3 is 6, minus 2 times 3 gives me, oh, let me erase that. So sorry, I've got 6 here. So 6 is row 3 minus 2 times 3. 6 times negative 6 gives me 0. And then my last one here, I've got 2 minus 2 times 1 gives me 0. So I have these zeros here. So we say the row of zeros indicates infinitely many solutions. Okay, and what that sort of usually will mean, or we're actually going to go through the definitions of that in a minute. So let's go, let Z equal T. So we're going to change in another variable. So we've got Z equals T now. So then we've got, therefore, negative 3y minus 1z equals 1. And we're going to change that to T. So we've got negative 3y minus 1t equals 1. So let's add T to both sides. So we get negative 3y. I keep forgetting my therefores. Okay, equals 1 plus T. And then we've got y equals, we're going to divide by negative 3. We're going to have negative 1/3. Take T. What? Have I stuffed up my solution again? I have to. Sorry, that negative 1 was wrong, so that's meant to be a positive 3. So, let's clean that up. So that makes all that wrong. That's why I'm looking at the text. Plus 3z. So we swap the z in for t. We get down to this plus 3 minus 3t, and we get negative 1/3 minus 3t over 3. The 3's there cancel out. And this becomes a positive here. So I'll remove that there. So that's our solution for that one. So now we can go to our next line up, which is x plus y take z equals 2. We sub our other values in. So we get, therefore, x plus negative 1/3 plus t minus our z value, which is t, equals 2. And so this is going to cancel out, and we're going to be left with the t's here will cancel. We take 1/3 from that. We add 1/3 to both sides, sorry, So we get 2 and 1/3, which is going to equal 7 over 3. So now we've got these. We've now got the solutions of this. So therefore, the solutions have the form x equals 7/3, y equals negative 1/3 plus t, and z equals t. And we've solved those, and just remember that t is just a real number, it's a constant. And so that's how we solve those ones there when you get that. We're going to go through what these mean a bit later, but that's all we've got for now.